At night, when a room seems silent, it is easy to imagine that sound has disappeared. The lights are low, the doors are closed, and the activity of the day has receded. Yet even then, the air is not truly empty. A faint current may move along the wall. Pipes may shift as they cool. Fabric may whisper when the body turns. Somewhere beyond the window, a distant vehicle passes, softened by glass and distance, until it becomes less an event than a change in the texture of the night. There are smaller sounds as well. Breathing has a rhythm. Clothing moves against skin. The floor responds gently to weight. The body itself produces subtle signals usually hidden beneath the louder world. Swallowing, the pulse carried through tissue, the small sounds of muscles adjusting. Most are not heard clearly for long. They appear at the edge of awareness and then fade, not because they have stopped, but because attention has moved elsewhere. This is one reason everyday silence is rarely the complete absence of sound. In ordinary life, silence is usually a comparison. A bedroom feels silent after a busy street. A forest clearing feels silent after conversation. An empty building may seem silent because no voices or footsteps are present, even though wind touches the windows and the structure settles around its own weight. A desert can feel vast and quiet while still holding moving air, distant birds, and the soft contact of sand against sand. What people call silence is partly acoustic and partly perceptual. It depends on how much sound is present, but also on what came before, what is expected, and which sounds the brain decides to emphasize. A steady hum may disappear from awareness after a few minutes. A clock may be noticeable at first and then seem to vanish. A sound remains, but it no longer receives the same priority. The brain is constantly sorting sound in this way. It does not treat every vibration as equally important. Some sounds matter because they are new, changing, close, or connected with familiar events. Others are repeated so often that they become part of the background. This filtering is not entirely conscious. It is an ongoing adjustment, shaped by the nervous system's effort to notice what matters without becoming occupied by everything. Even in quiet surroundings, the auditory system does not simply turn off. The ears continue receiving tiny changes in pressure, and the brain continues comparing incoming information with its expectations. It listens for patterns, interruptions, and signals that might deserve attention. Much of this monitoring happens without deliberate effort. A person may be resting while the brain still keeps a light watch over the acoustic world. This watchfulness does not mean that quiet is dangerous or that the brain is always tense. It means only that hearing is active even when very little seems to be happening. The auditory system is designed not merely to register sound, but to detect changes. A sudden noise can attract attention, but so can an unexpected absence. A refrigerator offers a simple example. Its low mechanical hum may continue long enough to become almost invisible to awareness. When the motor stops, the room may suddenly seem different. Nothing loud has occurred. In fact, there is less sound than before. Yet the change itself can be noticeable. For a brief moment, attention turns toward the new quiet. The same can happen when traffic fades unusually early, when rain pauses after falling for hours, or when a conversation stops at an unexpected point. The brain has been following a pattern, even if only faintly. When the pattern changes, awareness may rise for a moment to examine what has happened. This response is not necessarily fear. Often, it is simply orientation before attention settles again. Steady, familiar, low-level sound can sometimes feel more comfortable than a perfectly still acoustic space. The soft operation of a fan, distant rain, quiet ventilation, or muted city sounds may provide continuity. Because the pattern is predictable, the nervous system has less need to keep examining it. The sound becomes a stable background, neither demanding nor surprising. Absolute silence, or something close to it, can feel peaceful to some people and unfamiliar to others. In one setting, it may create spaciousness. In another, it may make internal sounds more noticeable or remove the usual cues that mark a place as familiar. Neither response is universal. Memory, personality, culture, expectation, and recent experience all shape the way quiet is interpreted. A rural night may feel calm to someone who knows it sounds well, while the same night may feel unusually open to a visitor accustomed to traffic. A quiet apartment may be restful after a long day, yet sudden silence in a normally active household may draw attention. The meaning of quiet depends not only on sound level, but on context. Peaceful, quiet, and uneasy silence are not fixed categories. They are different, possible experiences arising from the same ingredients: sound, attention, prediction, and meaning. The nervous system is sensitive not only to loudness, but also to uncertainty and change. A soft, stable environment may feel reassuring, while a quiet environment that seems unpredictable may hold attention more strongly. Research supports the broader idea that the brain uses expectations to interpret sensory information, though many details of how silence is experienced are still being studied. It is reasonable to think of quiet not as a blank condition, but as an active relationship between the world and the mind. The environment continues to offer subtle signals, and the brain continues to decide which should remain in awareness. So the silence of a room is not empty. It is layered with small sounds, softened patterns, and moments the brain has learned not to emphasize. Beneath apparent stillness, hearing remains awake in a gentle way, receiving, comparing, and filtering. What seems like nothing is often a finely balanced field of sound, expectation, and attention, waiting at the edge of notice. Sound begins as movement. Somewhere in the environment, an object vibrates, air pressure shifts, and a traveling pattern reaches the outer ear. The movement may come from a voice, a closing door, a branch rubbing against another branch, or the faint machinery inside a building. Even a very soft sound is a physical event before it becomes an experience. The outer ear gathers some of these pressure changes and guides them inward through the ear canal. At the end of that narrow passage sits the eardrum, a thin membrane that moves in response to the arriving pattern. Behind it, 3 very small bones pass the motion deeper into the ear. Their movement reaches the fluid-filled cochlea, where delicate sensory cells help convert mechanical vibration into electrical signals that the nervous system can use. This process is often described as hearing, but hearing is not completed in the ear. The ear collects and transforms information. The brain interprets it. It estimates where sound came from, whether it is near or far, whether it is familiar, and whether it should be brought into conscious attention. The experience of a quiet room is therefore created not only by what reaches the ear, but by how the brain organizes what arrives. At any moment, many sounds may overlap. A ventilation system may hum while fabric moves, a vehicle passes outside, and someone breathes nearby. The auditory system separates this mixture into possible sources. It does not receive a neat list of individual sounds. It receives a changing pattern and must make sense of it. To do this, the brain uses differences in timing, pitch, loudness, rhythm, and location. A sound arriving slightly earlier at one ear can help reveal its direction. A repeating frequency may be grouped into the steady tone of a machine. Brief or regular sounds may be treated as separate events. These operations occur rapidly and mostly outside awareness. In a calm environment, this sorting continues, even when there seems to be almost nothing to hear. The brain is still distinguishing the stable background from small changes within it. A soft hum may be classified as continuous and unimportant. A faint tap that occurs only once may receive more attention, even if it is quieter than the hum. This reflects an important feature of perception. The nervous system is highly responsive to contrast. A signal does not need to be loud in absolute terms to become noticeable. It may stand out because it differs from what surrounds it. In a noisy room, a small sound can disappear. In a quiet room, the same sound may seem clear and close. The surrounding pattern creates a kind of acoustic reference point. When the reference is steady, the brain can gradually reduce its response to repeated information. This is one reason familiar background sounds often fade from awareness. The process is sometimes described through ideas such as adaptation or habituation, although these terms refer to related processes rather than one simple mechanism. Adaptation can occur at different levels of the auditory system as responses adjust to ongoing stimulation. Habituation is a broader form of learning in which repeated, harmless events attract less attention over time. Together, such processes help explain why a sound that seemed obvious at first may later become difficult to notice without deliberately listening for it. A ticking clock illustrates this well. On entering a room, each tick may be distinct. After several minutes, the rhythm may seem to disappear. If attention returns to the clock, the sound becomes clear again. The ears did not stop receiving it. The brain simply gave it less importance, while nothing meaningful changed. This ability is useful because the world contains more sensory information than awareness can hold at once. If every steady sound remained equally prominent, attention would be filled with fans, distant engines, footsteps, air movement, and countless other repeating signals. By allowing predictable sounds to recede, the brain preserves room for events that may carry new information. Prediction is part of this filtering. The brain does not wait passively for each sound to arrive as if hearing the world for the first time. It uses recent patterns and past experience to form expectations about what is likely to happen. When the expected sound occurs, it can be processed efficiently. When something differs, the mismatch may briefly become more noticeable. A repeated sequence of soft sounds can create a strong expectation. If one sound is delayed, omitted, or replaced, the absence may be experienced almost like an event of its own. The silence is noticeable because the sound was expected to occupy that moment. This does not mean the brain literally hears a missing sound in the same way it hears a present one. Rather, the nervous system registers that the pattern has changed. The contrast between expectation and reality draws attention toward the gap. Such sensitivity can be observed in ordinary life. The regular vibration of a train may become background until it changes near a station. A distant appliance may be ignored until it stops. A person listening to steady rainfall may notice a pause before noticing any individual raindrop. The brain has formed a quiet model of what should continue. These internal models are flexible. They are revised as conditions change. When a fan switches off, the new silence may stand out for a few seconds. Soon, the quieter room becomes the new normal, and attention settles again. The auditory system updates its reference point. This helps explain why silence can deepen gradually. Immediately after loud activity ends, a room may feel strikingly still. After several minutes, the same room may no longer feel dramatically silent. Smaller sounds begin to emerge, and the brain adjusts to the lower level. The acoustic environment has not necessarily changed, but perception has. The opposite can also happen. After spending time in a quiet place, ordinary sounds may seem briefly stronger on returning to a busier environment. Hearing is always influenced by what came before. The nervous system compares the present with a recent sensory history. Attention adds another layer. A person can choose to listen closely to the room and discover sounds that had been present all along. The faint hum near a wall, the movement of air, or the distant passage of traffic may enter awareness simply because attention has turned toward them. Yet attention does not create these sounds. It changes which parts of the existing soundscape are given priority. Even deliberate listening has limits. Some sounds remain too faint, too continuous, or too blended with others to be clearly separated. The brain makes its best interpretation from incomplete information. Hearing is therefore both remarkably precise and quietly selective. Within apparent silence, this selection continues moment by moment. The ear receives movement, the brain organizes patterns, expectations form, and attention shifts. Quiet is not a pause in auditory processing. It is a condition in which the filtering becomes easier to notice, as small signals appear and disappear against a gentler background. The room may still seem empty of sound, yet beneath that impression is an active system measuring difference, continuity, timing, and meaning. Silence is shaped by what is present, what is faded from attention, and what the brain expects to hear. In a quiet place, the sounds that reach awareness are not always the loudest ones. Often, they are the sounds that differ most from the background. A faint creak in a still room may be more noticeable than a steady fan. A distant bird may emerge clearly during a pause in the wind, then seem to disappear when the leaves begin moving again. What becomes audible depends not only on the strength of a sound, but on the acoustic setting in which it appears. This setting is sometimes called a soundscape. It includes every sound within an environment, from the most obvious signals to the low, continuous textures that are rarely noticed directly. A room has a soundscape. So does a garden, a station, a shoreline, or a field before sunrise. Each one contains a mixture of sources, distances, rhythms, and spaces between events. The brain does not process this mixture as a flat wall of noise. It tries to organize it into separate streams. A voice is followed as one stream, while footsteps may form another. The low hum of a building becomes a stable layer beneath them. This ability is often described as auditory scene analysis. It allows the nervous system to make useful order from overlapping vibration. Several clues help with this organization. Sounds that begin and end together may be grouped as coming from the same source. Frequencies that change in a coordinated way may be heard as parts of one object or voice. Repeating rhythms create continuity. Location also matters. A sound arriving from the left side of a room can be separated from another sound coming from the right. Much of this sorting happens without conscious effort. The listener does not need to calculate timing differences between the ears or examine every frequency. The brain performs these comparisons automatically, building a practical impression of what is happening nearby. In a very quiet environment, there may be fewer streams to organize, but the process continues. The soft movement of air may form one layer. Distant activity may form another. The small sounds of the body may become more distinct because there is less external sound competing with them. Quiet does not remove the work of hearing. It changes the material being organized. Competition between sounds is important. When two sounds occupy similar ranges of frequency or occur at similar times, one may make the other more difficult to detect. This is known as masking. A low continuous sound can partly cover another low sound, while a brief sharp sound may be hidden by a louder event occurring at the same moment. Masking is common in daily life. The sound of running water can make distant speech harder to understand. Wind can cover the movement of leaves or small animals. A fan may soften the irregular noises of a building by blending them into a steadier background. The quieter sound has not vanished, but the auditory system has less information with which to separate it. This can help explain why gentle, continuous background sound sometimes makes an environment feel calmer. It may reduce the contrast created by small, unpredictable noises. A distant door closing, a pipe shifting, or footsteps in another room may blend more easily into the background rather than appearing as isolated events. The comfort does not come from sound alone. It comes from the relationship between the sound, the environment, and expectation. A steady background that is familiar and moderate may create continuity. Because it changes very little, it offers few surprises. The brain can classify it as part of the setting and allow it to remain outside the center of attention. Yet the same sound may not feel comfortable to everyone. A fan that one person barely notices may keep another person aware. A low mechanical hum may suggest familiarity in one building and feel intrusive in another. Sensitivity to sound varies, and experience can shape which patterns are easy to ignore. Attention also changes the effect of masking. A faint sound hidden within a background may become detectable when someone knows what to listen for. Musicians can sometimes follow one instrument within a complex arrangement. A person waiting for a familiar voice may recognize it in a crowded room. Expectation guides the brain towards certain features and helps separate them from the rest. This selective listening is sometimes described through the familiar example of noticing one's own name during a conversation elsewhere in the room. The brain appears able to monitor some unattended information, although the exact limits of this ability depend on the situation. Attention is selective, but it is not a perfect wall. Meaningful changes can sometimes cross into awareness. Quiet environments reveal this selectivity in a simpler form. A person may hear nothing in particular until attention is directed toward the farthest sound. Then perhaps a low vibration becomes noticeable. Attention shifts toward the nearest sound, and breathing or fabric takes its place. The soundscape seems to change. even though most of its physical features remain stable. This movement of attention is gentle but important. Awareness cannot hold every sound with equal clarity. It moves among possible signals, strengthening some and allowing others to recede. Silence is partly created by this recession. Sounds remain present, yet they are not selected strongly enough to shape the immediate experience. Predictability makes this easier. When the auditory system recognizes a stable pattern, it can devote fewer resources to examining each repetition. This does not mean the sound is ignored completely. Monitoring continues at a lower level, ready to respond if the pattern changes. A soft sequence of waves may settle into the background. The regular movement of a train may become almost unnoticed during a long journey. The repeated rhythm of footsteps can fade from awareness until the pace changes. Familiarity allows the brain to compress a stream of repeated events into a simpler expectation. Unpredictable sounds resist this process. If intervals vary, locations shift, or the character of the sound changes, attention may return more often. A single quiet tap repeated at irregular times can sometimes be harder to ignore than a louder but perfectly regular hum. The nervous system is not measuring volume alone, it is measuring uncertainty. This is why a quiet setting can contain both stillness and subtle activity. The acoustic level may be low, yet the brain remains responsive to changes within it. When the background is stable, awareness may broaden and settle. When a pattern breaks, attention narrows briefly toward the difference. The transition is often so quick that it passes without conscious thought. Most events are accepted as ordinary parts of the environment. Within that balance, silence is not an empty space between meaningful sounds. It is the wider field that allows differences to be noticed. It is shaped by masking, attention, familiarity, and the brain's quiet effort to separate the world into understandable sources. Even the calmest room holds layers, and hearing continues to move among them. Sometimes listening closely, and sometimes letting the whole scene soften into the background. When a sound changes, the brain often notices before conscious thought has had time to form. A steady tone becomes slightly higher. A repeating rhythm pauses. A soft hum shifts in intensity. These changes may be small, yet the auditory system is especially sensitive to differences that interrupt an established pattern. This sensitivity begins with a simple advantage. A stable environment can be represented efficiently. Once a sound is repeated long enough, the brain does not need to treat every moment as entirely new. It can form an expectation and compare incoming information with that expectation. When the sound continues as predicted, processing remains quiet and economical. When it changes, the difference receives more attention. Scientists have observed signs of this automatic comparison in measurements of brain activity. In carefully controlled experiments, a series of similar sounds is occasionally interrupted by one that differs in pitch, duration, or timing. The nervous system often produces a measurable response to the unusual sound, even when a person is not deliberately listening. Researchers sometimes describe this response using the term mismatch negativity. The name may sound more dramatic than the event itself. It does not mean that the unusual sound is emotionally negative or unpleasant. It refers to a pattern in electrical brain activity associated with detecting a difference between what was expected and what occurred. The finding supports the broader idea that the auditory system continuously compares present sound with recent regularities. This comparison can operate in quiet surroundings as easily as in noisy ones. If a room contains a stable hum, the hum becomes part of the brain's short-term model of the environment. If it stops, the new silence differs from that model. The absence may therefore attract attention, not because silence itself carries a warning, but because the pattern has changed. A familiar soundscape can be imagined as a soft collection of predictions. The ventilation continues. Distant traffic rises and falls within a known range. Floorboards respond in familiar ways. None of these expectations needs to be expressed in words. They are practical estimates formed through repeated exposure. When the environment behaves as expected, attention can remain elsewhere. Reading, resting, or simply allowing thoughts to drift becomes easier because the acoustic world requires little active examination. Predictability reduces the amount of new information arriving from moment to moment. This is one reason that loudness alone cannot fully explain whether a sound feels disruptive. A quiet but irregular noise may repeatedly attract attention, while a louder but steady sound may fade into the background. The nervous system responds strongly to novelty, contrast, and uncertainty as well as intensity. A drop of water falling at uneven intervals may be difficult to ignore because each pause leaves the timing unresolved. A clock with a regular rhythm may become less noticeable because every tick confirms the same pattern. The physical energy of the sounds may be similar, yet their predictability is different. The brain's response to change is often called an orienting response. When something new occurs, attention turns toward it briefly. The eyes may shift, the head may move slightly, or awareness may simply sharpen for a moment. This response helps identify the source and meaning of an event. In ordinary quiet, orienting responses are usually small and temporary. A pipe clicks as its temperature changes. A branch touches a window. A distant door closes. Attention rises, the sound is recognized as harmless or familiar, and the mind returns to its previous activity. Repeated exposure often reduces the response. If the same harmless sound occurs again and again, the nervous system may gradually stop treating it as new. This is another form of habituation. It allows attention to remain available for changes that are less familiar. Habituation is not permanent or complete. A sound may return to awareness if it becomes louder, changes location, or occurs after a long pause. The brain's model is always open to revision. It assumes continuity, but the quietest sounds a person can hear are not determined by the ears alone. They depend on frequency, distance, attention, health, recent exposure, and the background against which the sound appears. Hearing has no single boundary separating sound from silence. Instead, there are shifting thresholds, different for each kind of tone and each listening condition. Human hearing is generally most sensitive to frequencies that overlap with important features of speech. Sounds much lower or much higher Infrequency usually need more physical energy before they become noticeable. This means that two vibrations measured at the same intensity may not seem equally loud. One may be easy to hear, while the other remains close to the edge of perception. The edge itself is not perfectly stable. A faint tone may be heard on one occasion and missed on another. Attention may wander. Breathing may cover it for a moment. A distant vehicle may pass outside. Even the nervous system's own activity varies slightly from one moment to the next. Near the threshold of hearing, perception is less like a switch and more like a probability. In laboratory settings, researchers often present very soft sounds repeatedly to estimate the level at which a person detects them some proportion of the time. The result is useful, but it is not an absolute border. It describes performance under particular conditions, using particular sounds and equipment. Everyday listening is more complex because natural environments are full of overlapping signals and changing expectations. A room that seems silent may still contain sound below conscious awareness. Some vibrations are too faint to detect. Others lie outside the range of frequencies ordinarily heard. Some are masked by stronger signals or blended into the continuous background. The physical world remains active, even when the listener experiences stillness. At the same time, hearing is not merely a record of physical energy. The brain must decide whether an uncertain signal is present. When a sound is very faint, the available information may be incomplete. The nervous system combines sensory evidence with context and expectation, sometimes detecting a pattern clearly, and sometimes finding too little evidence to separate it from the background. Imagine waiting for a quiet sound that is expected to occur. Attention becomes directed toward the moment, and a subtle signal may be noticed more easily. Without that expectation, the same sound might pass unnoticed. This does not mean that expectation can create any sound at will. It means that the brain adjusts how carefully it examines uncertain information. The same principle operates in conversation. When a word is partly hidden by noise, knowledge of the sentence can help the listener understand it. The brain uses context to interpret the missing or unclear portion. Hearing is therefore constructive, though it remains anchored to incoming signals. Perception combines what arrives with what is already known. In quiet surroundings, there may be fewer external events to guide this interpretation. Attention can become more sensitive to small fluctuations. The faint buzz of an electrical device, the movement of air through a narrow opening, or the distant resonance of machinery may emerge gradually rather than appearing all at once. Once identified, the sound may seem obvious, even though it had been present for some time. Recognition changes listening. Before the source is known, a sound may seem vague or difficult to locate. After it is recognized, its pattern becomes easier to follow. The brain now has a model that helps organize the incoming information. A soft, irregular sound becomes the movement of a curtain. A low pulse becomes distant equipment. An uncertain rustle becomes leaves brushing lightly against glass. Naming a source is not always necessary for calm. Sometimes, it is enough that the sound behaves predictably and remains consistent with the setting. The nervous system can learn regularities without placing them into words. Familiarity grows through repetition, and the acoustic environment becomes easier to interpret. This learning happens over many timescales. Within seconds, the brain can become accustomed to a repeating pattern. Over days or months, it learns the usual sounds of a home, a workplace, or a neighborhood. Across years, people develop broad expectations shaped by climate, architecture, technology, and culture. Someone who has always lived near a railway may treat distant trains as part of the night. Someone accustomed to a rural setting may barely notice insects, wind, or early birdsong. Neither environment is objectively silent, yet each can support an experience of quiet because its sounds are familiar and easily understood. Moving to a new place can temporarily change this balance. Ordinary sounds may attract attention because their causes and rhythms are not yet known. Pipes may operate at unfamiliar hours. Elevators may produce low vibrations. Wind may move differently around the building. These sounds often become less prominent as the brain learns their patterns. The process is not guaranteed, and some sounds remain disruptive because they are too loud, irregular, meaningful, or personally unpleasant. Familiarity does not erase every response. It simply gives the brain more information about what is likely to happen and whether repeated monitoring is necessary. Meaning can outweigh intensity. A very soft sound connected with something important may attract attention immediately. A familiar signal, a nearby movement, or the beginning of a voice can stand out from a much louder background. The auditory system is shaped not only by physics, but also by learning and significance. This is especially clear when people listen for one particular sound. A parent may remain sensitive to movement in another room. A traveler may wait for an announcement. Someone expecting a visitor may notice footsteps outside. The same acoustic event might be ignored under different circumstances because its meaning has changed. Quiet, therefore, does not produce the same state of attention in every situation. Sometimes it permits attention to loosen because the environment is stable. Sometimes it sharpens listening because a meaningful signal is expected. The amount of sound may be nearly identical, while the mental relationship to that sound is entirely different. The body also contributes to this relationship. Breathing changes the sound near the ears. Posture alters the movement of clothing and the way vibrations pass through the body. Turning the head changes how sound reaches each ear and can make a distant source easier to locate. Listening is never completely separate from physical position. Even a still listener is not acoustically motionless. The chest rises and falls. Muscles make small adjustments. Air moves through the nose and throat. Most of these sounds are filtered from awareness during ordinary activity, but they may become clearer when the external environment grows quiet. Their appearance does not mean that silence has failed. It reveals that silence was never the removal of every vibration. It was a change in balance. External sounds receded, attention widened, and signals usually hidden beneath the day became available to notice. The boundary between sound and silence is therefore soft and movable. It shifts with the room, the body, the recent past, and the direction of attention. What seems silent from one moment may reveal a delicate structure in the next, not because the world suddenly became louder, but because listening became more finely tuned. A faint sound becomes easier to understand when the brain can place it somewhere. Even before its source is recognized, hearing begins estimating direction, distance, and movement. A small rustle may seem to come from the corner of a room. A low engine may appear far beyond the window. A brief tap may feel close because it reaches the ears clearly, with little softening from distance or reflection. This sense of acoustic space is built from tiny differences. A sound coming from one side usually reaches the nearer ear slightly earlier and often with slightly greater intensity. The head itself changes the sound before it arrives at the farther ear, reducing some frequencies more than others. These differences are extremely small. Yet, the nervous system can use them to form a practical estimate of direction. The shape of the outer ear contributes additional information. Its folds alter incoming sound in ways that depend on whether the source is above, below, in front, or behind. The brain gradually learns these patterns. Because the shape of each person's ears is slightly different, spatial hearing is partly calibrated through experience. Distance is more difficult to judge. A quiet sound may be far away, or it may simply come from a weak source nearby. The brain therefore combines several clues. High frequencies often fade more quickly over distance. Reflections become more important compared with the direct sound. Familiar objects also provide references. A known voice or a familiar door has an expected character, making changes in distance easier to estimate. In a quiet environment, these spatial clues may seem unusually clear. A single sound can reveal the dimensions of a place. One footstep in a hallway produces a different pattern from the same footstep in a furnished bedroom. A soft movement outdoors spreads into open space, while a movement indoors returns from nearby surfaces. The returning sound is known as reverberation. After the original vibration has been produced, reflections continue reaching the ears from walls, floors, ceilings, furniture, and other objects. In a heavily furnished room, much of the energy is absorbed quickly. In a large room with hard surfaces, reflections may continue for longer. These reflections are not usually heard as separate echoes. Instead, they blend with the original sound and give the room its acoustic character. A space can sound dry, warm, hollow, close, open, or resonant. Such descriptions are imperfect, but they express the way architecture becomes part of hearing. Even apparent silence carries a sense of space. A quiet room does not feel acoustically identical to an open field, although neither may contain a prominent sound. The smallest movement is shaped differently in each setting. Breathing near a wall returns faint reflections. Clothing moving in a narrow room creates a more enclosed pattern than the same movement beneath an open sky. The brain uses these subtle differences without requiring careful analysis. It constructs an impression of the surrounding space and updates that impression whenever new sound arrives. This helps explain why darkness does not remove all awareness of a room. Hearing continues to provide information about openness, boundaries, and distance. Sometimes, the acoustic impression of a place differs from its visual appearance. A room may look large but sound close, because curtains, carpeting, and furniture absorb reflections. A narrow stone passage may sound more expansive, because each movement lingers. The senses do not always describe space in the same way, and the brain combines their information into a single usable experience. When the environment is familiar, this combination becomes efficient. The usual reflections of a room are learned along with its ordinary sounds. A person may recognize a home from the way footsteps travel through it, even without consciously identifying the acoustic details. The sound of a key, a cupboard, or a distant door carries both information about the object and information about the surrounding space. Familiar spatial patterns can contribute to the sense that quiet is safe and settled. The brain knows where sounds normally come from and how they should behave. A low vibration from beyond a wall belongs to a known appliance. A soft movement overhead belongs to the ordinary structure of the building. Each event fits within an established model. In an unfamiliar place, the same level of sound may invite more attention. Reflections are different. Distances are uncertain. A sound that seems close may come from another floor or travel through a ventilation passage. The brain listens a little more carefully while it learns the acoustic map. This increased listening need not be uncomfortable. It may simply be a form of orientation. When entering a quiet hotel room, an old library, or an empty hall, awareness often expands briefly. Small sounds reveal surfaces and boundaries. After the space becomes familiar, many of those sounds recede. Movement helps build this map. Turning the head changes the timing and intensity of sound at each ear. A source that was difficult to locate may become clearer after a slight shift. The brain compares the changing pattern with its own movement and uses the difference to refine direction. This is one reason listening is an active process, even during stillness. The auditory system receives information from the environment, but it also relates that information to the position and motion of the body. Hearing belongs to a listener situated somewhere, facing one direction, surrounded by particular surfaces. The position of the body can alter the experience of quiet. Lying down changes the orientation of the ears and brings one side of the head closer to a pillow or mattress. Soft materials absorb some sounds while transmitting others through direct contact. A room heard from bed may seem different from the same room heard while standing. Some sounds also reach the inner ear through vibration conducted by bone and tissue rather than through air alone. This contributes to the way one's own voice is heard and helps explain why bodily sounds may become more noticeable in certain positions. Airborne and internally conducted vibrations combine into a single experience. Although their paths are different, most of the time, the brain does not separate these routes. It simply forms the best interpretation available. A sound is placed nearby or far away, inside the room or beyond it, connected with the body or connected with the environment. These judgments are usually reliable, but they are not perfect. Reflections can make a source seem displaced. Low frequencies can travel through walls and lose the details that reveal their origin. A faint sound may appear to move as the listener changes position. In quiet surroundings, such uncertainty may hold attention for a moment, until a likely explanation is found. Once the pattern becomes understood, attention often softens again. The room returns to being a coherent space rather than a collection of uncertain signals. Its walls, openings, surfaces, and distant boundaries are quietly represented through sound. Silence, therefore, has a shape as well as a level. It can feel enclosed or wide, near or distant, softened or resonant. These qualities arise from the interaction between vibration, architecture, movement, and the brain's continuing effort to locate itself within the surrounding world. The experience of quiet is shaped not only by what the ears receive, but also by the state of the body that is listening. The same room can feel deeply peaceful at one time and unusually noticeable at another. Its walls, furniture, and background sounds may remain unchanged, while attention, expectation, and physical readiness quietly alter the way the environment is perceived. The nervous system is always adjusting its level of responsiveness. During focused activity, some sounds are pushed toward the background, During rest, attention may become broader and less tightly directed. In an unfamiliar setting, hearing may remain slightly more watchful until the ordinary patterns of the place have been learned. This watchfulness is not necessarily conscious. A person does not need to examine every sound or decide whether it matters. Much of the sorting happens automatically. Familiar signals are allowed to pass with little interruption, while sudden or uncertain events receive a brief increase in processing. The response can be very small. Awareness may sharpen for less than a second. Breathing may pause almost imperceptibly. Muscles may make a slight adjustment before the sound is identified. These reactions belong to the general process of orientation, in which the body and brain turn toward new information. Orientation is different from fear. It is a neutral form of attention that helps the nervous system answer a simple question: has something changed? Most of the time, the answer is ordinary. A floorboard has shifted with temperature. Water has moved through a pipe. A vehicle has passed outside. Once the event fits the setting, attention can settle again. In stable quiet, these moments may be widely separated. The acoustic environment offers little that is new, and the brain has no reason to keep bringing sound into the foreground. This can create a sense of spaciousness. Awareness is still open, but it is not being repeatedly interrupted. A gentle background sound may support the stability. The low movement of air, steady rain, or distant traffic can create a continuous reference. Small changes occur within it, but the overall pattern remains familiar. The soundscape provides evidence that the environment is continuing in its usual way. The comforting quality of such sound is not guaranteed. It depends on volume, personal sensitivity, meaning, and context. A low hum that seems neutral in one room may be irritating in another. Rain may feel soothing when it is soft and expected, yet distracting when it strikes an unfamiliar surface in an irregular rhythm. Still, predictability often makes sound easier to place outside the center of attention. The brain can form a simple expectation and devote less effort to examining each repetition. The background becomes part of the environment's steady identity. Sudden silence can interrupt that identity. When irregular sound stops, the nervous system receives less acoustic energy, but more new information. The change may be noticed precisely because the previous sound had become so familiar. Consider a room containing a quiet air conditioner. After a while, the sound is no longer prominent. It becomes a broad, soft layer beneath everything else. When the machine switches off, the room may seem to open. The change is clear. Even though the new condition is quieter, for a brief period, attention may search for the meaning of the pause. Has the machine completed its cycle? Has the power changed? Is the room simply entering its usual interval of stillness? These possibilities may not appear as words. Recognition can happen quickly, below deliberate thought. Once the silence is understood, it may become peaceful. The refrigerator has stopped because the desired temperature was reached. The rain has paused because the cloud has passed. The traffic has faded because the hour is late. The gap finds a place within a larger pattern. When the reason is unclear, attention may remain engaged a little longer. This does not mean that the silence is harmful. It means that uncertainty has not yet been resolved. The brain continues listening because it has not learned whether the new condition is temporary, meaningful, or simply unfamiliar. Context gives silence much of its emotional character. A pause in a quiet library is ordinary. A pause in music may be expressive. A sudden stop during conversation may carry social meaning. The physical absence of sound can be similar, while the interpretation is entirely different. Memory helps provide that interpretation. Previous experiences teach the nervous system which silences belong to safety, concentration, privacy, waiting, distance, or interruption. These associations are personal, but they are also shaped by shared habits and cultural expectations. Some households are naturally quiet. Others are filled with conversation, movement, appliances, or sounds from nearby streets. A person raised with steady background activity may experience complete stillness as unusual. Someone accustomed to long periods of quiet may find the same stillness familiar and unremarkable. Neither response is more correct. The brain builds its expectations from repeated experience. What feels peaceful is often what can be understood easily, rather than what has the lowest possible sound level. This is why acoustic comfort cannot be measured by loudness alone. A quieter environment is not always perceived as calmer, and a gentle sound is not always perceived as disturbance. Rhythm, control, familiarity, timing, and meaning all contribute. A sound that can be anticipated may be easier to ignore than one that appears unpredictably. A background chosen voluntarily may feel different from an identical sound that cannot be changed. A distant voice may be pleasant when its words are indistinct and distracting when fragments become understandable. Small changes in meaning can alter the amount of attention a sound receives. The body's condition also changes this balance. Fatigue, concentration, emotional state, and recent exposure to noise may influence sensitivity. After a busy period, ordinary quiet may feel like a strong contrast. After many hours of stillness, a small sound may seem more prominent than it otherwise would. These variations do not imply that the auditory system is unreliable. They show that hearing is adaptive. Its purpose is not to provide a fixed meter reading of the world. It helps the listener function within changing surroundings by emphasizing what is likely to matter in that moment. Quiet allows this adaptive system to be observed in a subtle form. There may be no dramatic sound, only a soft background, a brief pause, and a gradual return to stillness. Yet within that simple sequence, the brain compares patterns, checks expectations, searches for meaning, and adjusts the level of attention. The silence that follows a familiar sound is therefore more than an empty interval. It is a new sensory condition being tested against memory. As understanding grows, the nervous system can release the change from the foreground, allowing the room to become quiet once more. Attention does not simply increase or decrease hearing as a whole. It changes which sounds are allowed to become clear. In a quiet room, several gentle signals may be present at once: the movement of air, the distant sound of plumbing, a vehicle far beyond the window, and the rhythm of breathing. Awareness rarely holds all of them with equal detail. Instead, it moves among them, selecting one pattern while allowing others to soften. This selection can be voluntary. A person may decide to listen for the farthest sound in the environment or notice the faintest sound within the room. Almost immediately, the soundscape seems to reorganize. A low vibration that had gone unnoticed becomes distinct. The softest movements gain edges. Signals that were present all along begin to feel newly discovered. Attention can also be captured automatically. A sudden change, an unfamiliar rhythm, or a sound connected with personal meaning may enter awareness without invitation. The brain shifts toward it before there has been any conscious decision to listen. This movement is usually brief. If the event proves ordinary, attention returns to whatever came before. The auditory system, therefore, balances two broad forms of listening. One is guided by current goals and interests. The other is drawn toward changes that may deserve examination. Scientists often describe these influences as top-down and bottom-up attention. The terms refer to different directions of control rather than separate systems working in isolation. Top-down attention begins with expectation or intention. Someone listening for a particular voice can follow it more easily among other sounds. Someone waiting for a quiet signal may detect it sooner. The brain gives greater priority to features that are likely to carry the desired information. Bottom-up attention begins with the sound itself. A sudden tap, an unexpected pause, or a shift in pitch may stand out because it differs from the background. No deliberate search is required. The event creates enough contrast to rise into awareness. Most ordinary listening involves both. A person may be focused on reading while the brain continues monitoring the room. The steady sounds remain in the background, but an unusual change can still interrupt. After the change has been identified, deliberate attention may examine it more closely or allow it to fade. This flexibility helps explain why quiet can support concentration without eliminating awareness of the surroundings. A stable soundscape places fewer demands on attention. Because little is changing, the brain does not need to redirect itself as often. Yet hearing remains available, ready to respond when the pattern becomes different. The filtering is not perfect. Attention can be tired, divided, or drawn repeatedly toward irrelevant sounds. A very faint, irregular noise may become difficult to ignore once it has been noticed. The brain begins expecting its return, and each uncertain pause can keep the sound mentally active. This is one reason that anticipation sometimes makes a quiet sound feel more prominent. Once the pattern has been identified, awareness may continue checking for it. The sound is no louder than before, but its place in attention has changed. It now has a history and an expected future. If the sound becomes regular, it may gradually recede again. The nervous system learns its timing and character. Each repetition provides less new information. What was once a distinct event becomes part of the background. Attention can also change the apparent boundaries of silence. When it is directed outward, the room may seem filled with distant layers. When it turns toward a single task or thought, those layers may almost disappear. The physical environment remains similar, yet the experience of quiet becomes narrower or wider. This is not unusual. Perception is always selective. Vision does not preserve every object with equal clarity, and touch does not keep clothing constantly in awareness. Hearing follows the same general principle. Stable information is often reduced so that changing or relevant information can be emphasized. The brain performs much of this filtering across several stages. Early auditory pathways respond to basic features such as timing and frequency. Higher regions help organize sounds into sources, recognize familiar patterns, and connect them with meaning. Attention can influence processing at more than one level, strengthening some signals while reducing competition from others. The exact mechanisms are complex, and research continues to refine how these networks cooperate. There is no single place where unwanted sound is simply switched off. Filtering emerges from many interacting processes, including sensory adaptation, learned expectation, memory, and the shifting priorities of attention. This distributed system allows listening to remain sensitive without becoming overwhelmed. It can preserve a broad awareness of the environment while bringing one source into focus. It can reduce a repeating hum, follow a voice, detect an interruption, and then return to stillness. Quiet makes these movements easier to notice because there are fewer strong signals competing for awareness. A distant sound can be followed until it fades. A soft vibration can appear gradually. The mind can move from one layer to another without the urgency created by louder surroundings. Yet quiet does not always produce focused attention. Sometimes it allows thoughts to wander, and external sound becomes less prominent. Sometimes it reveals small noises that hold attention more strongly than expected. The direction depends on the setting, the listener's purpose, and the balance between familiarity and uncertainty. A familiar room often supports a wide, relaxed form of listening. Its sounds are known well enough that they do not require constant inspection. Awareness can remain open without fastening onto every detail. The room is heard as a whole rather than as a series of separate events. In an unfamiliar room, listening may be more precise at first. Each small sound offers information about the space. The hum of ventilation, the movement beyond a wall, and the timing of distant footsteps help build an acoustic picture. As the pattern becomes understandable, the separate details begin to merge into a stable background. This merging is part of what makes a place feel quiet. Silence is not created only by reducing sound. It can also arise when the sounds that remain no longer compete strongly for attention. They become organized, predictable, and easy to interpret. The result is a form of perceptual simplicity. The world is still present, and the ears are still receiving information, but very little demands an immediate response. Sound continues at the edges of awareness, gently confirming the shape and continuity of the surroundings. Within the simplicity, the brain remains active but not necessarily occupied. It listens broadly, notices changes, and lets familiar patterns recede. Quiet emerges from this careful balance. Enough monitoring to remain connected with the environment, and enough filtering to allow most of that environment to remain softly in the background. The way quiet is experienced also depends on how prepared the nervous system is to respond. Hearing does not operate at exactly the same level of sensitivity throughout the day. Attention rises and falls. The body shifts between activity and rest. Expectations change from one setting to another, and these changes influence how easily a sound enters awareness. In a familiar, stable environment, the brain may treat most background information as already understood. The soft movements of a building, the distant pattern of traffic, and the repeated operation of appliances require little examination. They are recognized as ordinary features of the surroundings and allowed to remain at the edges of perception. In a less familiar environment, the same kinds of sounds may receive more attention. Their sources have not yet been learned, and their timing is uncertain. A quiet mechanical sound may appear, stop, and return. A faint movement beyond a wall may be difficult to place. The nervous system gathers these details gradually, building a model of what belongs in the new setting. This process can be thought of as acoustic learning. It is rarely deliberate. Over time, the brain becomes familiar with the usual range of sounds, their locations, and their rhythms. It learns which signals repeat harmlessly and which changes are unusual enough to examine. As this knowledge grows, the environment often feels quieter, even if its measured sound level remains the same. The difference lies in interpretation. Fewer events seem new. Fewer patterns require active attention. The soundscape becomes easier to predict. Predictability is closely connected with a sense of control, although the two are not identical. A sound may be predictable even when it cannot be changed, and a controllable sound may still be surprising if it begins unexpectedly. Yet both predictability and control can influence how much attention the nervous system gives to an acoustic event. A sound produced by one's own movement is often processed differently from a similar sound coming from an unknown source. When a hand places an object on a table, the brain has information about the intended action before the sound occurs. It can anticipate roughly when the contact will happen and what kind of sound it may create. This anticipation can reduce the surprise of the event. The sound is still heard, but it fits a prediction connected with movement. By contrast, the same tap occurring without an obvious cause may attract more attention because its timing and source were not expected. The brain receives signals from systems involved in planning movement and uses them to help interpret the sensory consequences of an action. Researchers sometimes describe this as an internal prediction of self-generated sensation. It contributes to the familiar difference between creating a sound and merely receiving it. Footsteps offer a simple example. The sound of one's own steps usually blends with the rhythm of walking. Each contact with the ground is closely linked to movement and timing. Another person's footsteps, especially when their location or rhythm is unclear, may remain more noticeable because they are not predicted in the same way. Breathing also has this self-generated quality. Its sounds are usually filtered efficiently because they are continuous, familiar, and connected with bodily signals. In ordinary surroundings, breathing rarely occupies attention for long. In deeper quiet, however, the reduction of external sound can make it more distinct. This change does not mean that breathing has suddenly become louder. Its relationship to the background has changed. There is less masking, and attention has fewer competing signals. What was previously hidden becomes easier to notice. The same is true of many small bodily sounds. Swallowing, clothing shifting, joints moving, and the gentle contact between the body and a chair or bed may all appear more clearly in quiet conditions. They belong to the ordinary soundscape of being alive, though they are often covered by the activity of the surrounding world. brain generally recognizes these sounds as self-related and familiar. It combines hearing with information from touch, movement, and internal sensation. A rustle is understood not merely as an external noise, but as the result of fabric moving with the body. This combined information helps place the sound within a stable explanation. When a sound has no clear explanation, the brain may continue examining it. It may compare the event with memory, wait for it to repeat, or use small changes in position to estimate its source. Once a likely cause is identified, the sound often loses some of its power to hold attention. This illustrates how uncertainty can influence listening. A faint known sound may be easy to ignore, while an equally faint, unidentified sound remains present in awareness. The difference is not simply emotional. It reflects the amount of unresolved information carried by the event. The nervous system is constantly attempting to reduce this uncertainty. It groups sounds into sources, compares them with familiar patterns, and estimates what is likely to happen next. Most of these estimates are ordinary and temporary. They help the world remain coherent from one moment to the next. Quiet can make this predictive work more visible. In a busy setting, changes occur so frequently that no single small event may stand out for long. In a quiet setting, a subtle sound can be followed from its beginning to its end. Its location, duration, and repetition become easier to observe. A low creak may begin as wood responds to temperature, continue for a moment, and then fade into stillness. The brain may recognize it from many previous nights. Because it fits a familiar pattern, it is quickly returned to the background. A different sound may invite a little more attention. Perhaps it occurs at an unusual time or from an unexpected direction. Awareness turns toward it, waits briefly, and then settles when nothing further changes. The process is gentle and often barely noticed. The body's broader state can influence how readily these shifts occur. When attention is already highly engaged, small sounds may not enter awareness at all. When a person is resting quietly, the listening field may widen. When uncertainty is present, the threshold for noticing change may become lower. These changes are normal parts of an adaptive system. Hearing is not equally open to every signal at every moment. It adjusts to current needs, recent experience, and the amount of information available from other senses. This is why quiet can feel expansive without being empty. With fewer dominant sounds, the brain can notice subtle relationships between movement, space, and expectation. A small noise appears, finds its place within the environment, and fades again. Each fading sound leaves behind a slightly clearer model of the surroundings. The room remains where it was. Its familiar sources continue their patterns. The nervous system keeps listening, but much of what it hears has already been understood. In this way, calm quiet often depends less on the disappearance of sound than on the disappearance of uncertainty. The environment becomes gentle, not because nothing is happening, but because what is happening feels known, continuous, and easy for the brain to place. As an environment grows quieter, hearing does not remain fixed at a single setting. The auditory system adjusts to the level of sound that has been present. After leaving a busy street and entering a quiet room, the first impression may be one of deep stillness. A few minutes later, however, sounds that were initially hidden begin to emerge. Air moves through a vent. A clock becomes distinct. activity from another floor appears at the edge of awareness. The room has not necessarily become louder. Instead, the relationship between its sounds and the listener's recent experience has changed. The nervous system is no longer comparing the room with the same intense background. It is gradually adapting to a lower acoustic level and becoming more responsive to small differences within it. This adjustment is part of the wide range over which hearing must operate. Human ears can respond to very faint sounds while also functioning in much louder surroundings. No single level of sensitivity would work equally well in every setting. The auditory system therefore modifies its responses as conditions change. Some of this adjustment begins within the sensory structures of the ear, while other parts occur along pathways in the brain. Researchers sometimes use the broad idea of auditory gain to describe how strongly sound information is represented. The comparison is similar to adjusting the sensitivity of a receiving system, though biological hearing is far more complex than a simple volume control. In a louder environment, reducing sensitivity to continuous stimulation can help preserve useful differences and prevent every strong sound from dominating in the same way. In a quieter environment, greater responsiveness can make weak signals easier to detect. These adjustments occur across different timescales, from rapid changes lasting moments to slower changes shaped by longer exposure. The result can be felt during an ordinary transition into quiet. At first, the silence seems broad and nearly featureless. Gradually, it develops texture, sounds separate from one another. The distant becomes more distinct, and the small movements nearby seem to gain clarity. This does not mean that hearing improves without limit as the environment becomes quieter. Every sensory system has boundaries. Some vibrations remain too faint, and some are obscured by activity within the body or nervous system itself. Silence does not create perfect access to every acoustic event. It simply reduces some of the competition. Even highly controlled quiet spaces contain limits. Laboratories can build rooms with thick walls and carefully designed surfaces to reduce external sound and reflections. Such spaces may approach a level of quiet rarely experienced in daily life, yet a person inside them does not encounter complete sensory emptiness. Breathing remains. Small body movements remain. The flow of air and subtle vibration through tissues remain. Equipment and building materials may contribute extremely faint signals. The nervous system also has its own ongoing electrical activity, which does not stop when external stimulation decreases. Ordinarily, this internal activity is not experienced as a separate sound. Perception depends on patterns, strong and organized enough to be distinguished from the background activity of the system. A faint external signal must stand out from both environmental noise and the natural variability of neural processing. This is one reason the threshold of hearing is not perfectly sharp. Near the lowest detectable levels, a sound may be noticed during one presentation and missed during another. The evidence available to the brain is uncertain. It must decide whether the pattern came from the outside world or whether there was too little information to identify anything clearly. Expectation can gently influence this decision. When the time and character of a faint sound are known, attention can be directed toward the relevant moment. Detection may become more likely because the brain is prepared to examine a particular pattern. When no sound is expected, the same weak signal may remain outside awareness. Preparation does not replace sensory information. It changes how that information is evaluated. The brain combines the strength of the incoming signal with knowledge about what might reasonably occur. This is a general feature of perception, not a special property of silence. The effect is familiar when someone listens for a distant sound at night. At first, nothing seems present. After a few moments, a repeated vibration becomes noticeable. Once its timing is understood, each occurrence is easier to follow. The brain has learned where and time to listen. If the pattern stops, the pause may seem unusually clear. Expectation continues for a moment beyond the final sound. The missing repetition creates a contrast between what the brain prepared to receive and what actually arrived. The silence after a pattern can therefore feel different from the sounds before it. Before the sound began, there was no established rhythm. After it ends, an expectation remains briefly active. The acoustic level may be the same in both moments, but perception carries a memory of what has just occurred. Music often makes careful use of this principle. A pause gains meaning from the sound surrounding it. The physical silence may last only a moment, yet it is shaped by rhythm and anticipation. Everyday environments contain simpler versions of the same relationship. Rain pauses between gusts of wind. Footsteps stop beyond a doorway. A machine completes its cycle and leaves the room still. In each case, the quiet is defined partly by the pattern that preceded it. The brain does not erase recent sound immediately. It carries a short record forward, allowing new events to be compared with the recent past. This brief sensory memory helps connect separate moments into a continuous soundscape. Without such continuity, every sound would arrive as an isolated event. A rhythm could not be recognized, a voice could not be followed smoothly, and a pause could not be experienced as an interruption. Sounds becomes meaningful because hearing preserves enough of the past to recognize what has changed. As time passes, the short-lived expectation fades. The missing sound is no longer treated as something that may return at any moment. The quieter condition becomes the new reference, and other subtle signals begin to take its place. A room once dominated by a fan may reveal distant traffic after the fan stops. When traffic fades, the quiet movement of the building may become clearer. If those sounds also recede, breathing and fabric may enter awareness. There is rarely one final layer beneath which nothing remains. Attention simply moves toward progressively softer patterns. This changing sensitivity gives quiet its depth. Silence can seem simple from a distance, yet prolonged listening reveals several levels of sound, each becoming noticeable as stronger layers disappear or lose importance. The auditory system adjusts continuously, preserving contact with the environment without requiring every signal to remain equally clear. What appears to be stillness is therefore a living balance between the strength of sound and the sensitivity of hearing. The world grows quieter, the nervous system adapts, and a finer acoustic landscape slowly comes into view. The first moment of a sound often carries more information than the sound that follows. A hum beginning, a branch shifting, or a voice entering a quiet room creates a clear boundary between one condition and another. The auditory system is especially responsive to these boundaries because they mark change. They suggest that a new source has appeared, that an existing source has moved, or that the environment has entered a different state. The ending of a sound can be just as informative. When a steady pattern stops, the brain receives evidence that something has changed, even though no new vibration has replaced it. The transition from sound to quiet becomes an event in perception. It has timing, context, and a relationship to what came before. This sensitivity to beginnings and endings helps the brain organize the acoustic world. A continuous stream of vibration must be divided into meaningful pieces. One sound begins, another overlaps it, and a third fades slowly into the background. The nervous system uses these changes to estimate which signals belong together and which come from separate sources. A soft mechanical hum may remain stable for many minutes. During that time, its beginning is no longer present, and the brain has little new information to examine. The sound becomes familiar. When it stops, a fresh boundary appears. The change is small in physical energy but clear in structure. In this way, hearing is often more concerned with differences than with unchanging conditions. The auditory system responds to the shape of change across time. A sound that rises gradually may be treated differently from one that begins sharply. A fading sound may suggest increasing distance, reduced activity, or the end of an event. The brain learns many of these patterns through ordinary experience. Footsteps approaching usually become clearer and stronger. A passing vehicle follows a familiar rise and fall. A door produces a brief sequence of movement, contact, and stillness. These patterns help the nervous system predict not only what a sound is, but how it is likely to develop. Prediction allows perception to remain smooth. The brain does not need to reconsider the identity of a familiar source at every moment. Once a pattern is recognized, much of what follows can be anticipated. Attention may then move elsewhere, while lower levels of the auditory system continue monitoring the sound. If the expected pattern changes, awareness may return. Footsteps stop earlier than usual. A motor changes speed. Rain shifts from a steady texture to a few separate drops. The difference invites a new interpretation. Most of these changes are minor. They do not produce a strong emotional response. They simply create information. The nervous system notices, compares, and updates its model of the surroundings. This updating depends on timing. Hearing is remarkably sensitive to when events occur. Very small differences help reveal rhythm, direction, distance, and the separation between sources. The brain tracks these differences across milliseconds, although the listener experiences the result as a natural and continuous world. Timing also shapes the spaces between sounds. A short pause may be heard as part of a rhythm, while a longer pause may suggest that the sequence has ended. The physical absence of vibration is similar in both cases, but its duration changes the meaning. A clock provides a simple pattern. The interval between ticks becomes familiar through repetition. If one interval lasts slightly longer, attention may rise before the next tick arrives. The brain has learned not only the sound itself, but the expected length of the silence surrounding it. The spaces are therefore part of the sequence. Without them, separate ticks would merge into a continuous tone. Without pauses between words, speech would lose much of its structure. Without intervals between events, the soundscape would be harder to divide into understandable moments. Silence helps create boundaries. It separates one sound from another and gives each event a beginning and an end. Even in a place that is not especially quiet, brief gaps allow the auditory system to organize what it hears. These gaps may be extremely small. In conversation, The brain uses subtle pauses, changes in pitch, and shifts in rhythm to follow meaning. In natural environments, it uses intervals to separate calls, movements, and distant activity. The spaces are rarely noticed directly, yet they help shape the whole experience. A quiet room contains longer and more visible intervals. A pipe clicks once and then remains still. A vehicle passes and leaves a soft absence behind it. A movement of fabric ends, allowing the room's background to return. The background itself is not perfectly constant. It fluctuates gently. Airflow changes. Distant activity rises and falls. The body shifts position. The auditory system must decide which fluctuations belong to continuing sources and which signal something new. This decision is not always exact. A faint sound may be interpreted differently depending on context. A low vibration might seem mechanical in one setting and distant traffic in another. The brain chooses the explanation that best fits the available evidence and remains ready to revise it. Perception is therefore a quiet form of inference. The nervous system receives incomplete patterns and estimates their most likely causes. It uses frequency, timing, location, memory, and expectation to build a stable acoustic world. Usually, this process is so efficient that the interpretation feels immediate. A sound seems simply to be a sound from somewhere. The complex work of grouping and prediction remains hidden. In deep quiet, however, uncertainty can become easier to notice. A distant signal may not reveal its source at once. It may appear as a soft pulse, a low resonance, or a brief change in the room. Attention waits for another example, gathering enough information to make the pattern clearer. If the sound repeats, its identity may slowly emerge. If it does not return, it may remain unresolved and then fade from thought. Not every event needs a complete explanation. The brain often accepts a likely interpretation and releases the rest. This ability to release uncertainty is part of ordinary listening. The nervous system does not continue investigating every faint sound indefinitely. When an event is weak, isolated, and followed by stability, its importance usually declines. The surrounding quiet helps with this decline. Nothing further occurs to strengthen the signal. The room returns to its familiar pattern, and attention broadens once again. A sound has begun, changed the acoustic scene for a moment, and ended. The brain has marked its boundaries, compared it with memory, and allowed it to pass. What remains is not an empty gap, but the steady background against which another small event may eventually appear. Every environment has a kind of acoustic floor. It is the soft level beneath the more obvious events formed by air movement, distant activity, electrical systems, weather, and the countless small vibrations of the surrounding structure. In an ordinary room, this background is rarely noticed as a collection of separate sounds. It is heard more often as the general tone of the space. Sound engineers sometimes call this room tone. When a room is recorded between spoken sentences, the recording is not completely empty. It contains the low, continuous character of that particular place. A microphone may capture ventilation, faint traffic, electrical hum, and reflections too subtle to attract attention during normal listening. If a recording suddenly replaces this background with perfect digital silence, the change can sound unnatural. The absence may be more noticeable than the room tone itself. Although the background was not consciously important, it provided continuity. Removing it creates a sharp boundary that the auditory system can detect. Daily life contains a similar continuity. A home has a quiet acoustic signature. A forest has another. Even two rooms in the same building differ slightly because of their size, surfaces, airflow, and position in relation to the outside world. These signatures are not fixed, but they remain stable enough for the brain to learn. The sound floor rises and falls throughout the day. Morning activity adds distant movement. Wind changes the pressure around windows. Heating systems begin and stop. At night, some layers disappear, while others become easier to notice. What is called silence may simply be the quieter phase of this changing background. The exact level of sound can be measured, but a measurement alone does not describe the full experience. Sound level is often expressed in decibels, a scale designed to represent a very wide range of physical intensities. The scale is logarithmic, which means its numbers do not increase in a simple one-to-one way with acoustic energy. Yet even a precise decibel reading cannot reveal whether a place will feel peaceful. Two environments with similar average levels may be perceived very differently. One may contain a smooth, steady background. The other may contain long, quiet intervals interrupted by irregular sounds. Their measured averages can be alike, while their patterns place different demands on attention. Frequency also matters. A low rumble, a high tone, and a broad mixture of many frequencies can produce different experiences at similar measured levels. The human ear is more sensitive to some frequencies than others, and the brain assigns different meanings to different patterns. Duration changes perception as well. A short sound may pass without difficulty, while a repeating sound at the same level may gradually become prominent. Alternatively, repetition may make the sound easier to ignore if its timing and character are stable. The outcome depends on how predictable the pattern becomes, and whether it continues to carry useful information. This is why silence cannot be defined by one universal number. In science and engineering, quiet conditions can be described using physical measurements and agreed standards. In ordinary experience, however, silence remains partly relational. It depends on comparison, expectation, and the way sound is distributed through time. A library may be considered quiet even when pages turn, chairs move, and ventilation continues. These sounds fit the purpose and character of the place. They are usually soft, separated, and understandable. Their presence does not necessarily disturb the impression of silence. A house during the early morning may feel silent, while birds call outside and pipes move within the walls. The sounds are present, but the wider pattern remains spacious. No single event dominates for long, and many of the signals are familiar. By contrast, one isolated tone can make a physically quiet space feel less silent. Because the surrounding level is low, the tone stands out clearly. Its narrow frequency and steady presence may hold attention even when it contains little acoustic energy. The difference can be understood through signal and background. A sound becomes noticeable when it can be distinguished from what surrounds it. Lowering the background may reveal signals that were always present. Raising the background may hide them, even though their physical intensity has not changed. This relationship is known broadly as the signal-to-noise ratio. In this use, noise does not necessarily mean an unpleasant sound. It refers to the other acoustic activity against which a particular signal must be detected. A voice can be clear in a quiet room and difficult to understand beside running water, because its relationship to the background has changed. The brain continuously estimates these relationships without calculating them consciously. It identifies patterns that rise above the sound floor, follows them while they remain useful, and allows them to merge back into the background when their information becomes repetitive. In a stable environment, the acoustic floor becomes a reference. A new sound is judged against it. A faint event may stand out clearly if the background is smooth. The same event may disappear if the background is changing in a similar range of frequencies. Quiet, therefore, increases contrast. It does not only reduce stimulation, it can make small events more distinct. The click of cooling metal, the movement of fabric, or the distant closing of a door may seem unusually precise because there is little around it to blur its edges. This increased clarity can be pleasant when the sounds are familiar and widely spaced. Each event appears gently and then fades. There is enough room between sounds for the auditory system to return to its stable reference. When sounds are uncertain or irregular, the same clarity may keep attention more active. The brain can follow each event easily, but it may not yet know how the events fit together. As the pattern becomes familiar, their prominence often decreases. The acoustic floor itself may then return to awareness as a unified whole. Rather than hearing ventilation, distant roads, and moving air as separate sources, the listener experiences the quiet character of the room. Individual layers are blended into a continuous setting. This blending is one of the subtle achievements of perception. The brain preserves enough information to detect change while allowing countless stable details to remain unexamined. It creates a coherent background without losing the ability to separate a new signal from it. Silence emerges within that background, not outside it. It is the sense that the acoustic world is steady, spacious, and asking little from attention. The room still has a tone. The air still carries vibration, and hearing still follows the smallest changes. But most of the surrounding pattern has settled into an undemanding whole. Quiet is often described as calming, but the relationship between sound and calm is more subtle than a simple rule. A low sound level does not automatically place the nervous system at rest. Just as the presence of sound does not automatically create tension, the effect depends on whether the environment feels understandable, stable, and appropriate to the moment. The nervous system continually adjusts the body to changing conditions. Some of these adjustments support activity and alertness. Others support rest, digestion, and recovery. Sound can influence this balance. Because hearing remains connected with broader systems involved in attention, movement, and physiological readiness. A sudden sound may briefly increase alertness. Attention turns toward the source. Muscles may prepare for movement, and the heart may change its rhythm slightly. These reactions can occur before the sound has been fully identified. Once it is recognized as ordinary, the response usually fades. The size of the response depends on many features. Loudness matters, but so does speed, novelty, location, timing, and meaning. A moderate sound that begins abruptly can attract more attention than a somewhat louder sound that rises gradually. An unexpected sound close by may be processed differently from a familiar sound at a distance. Silence can influence alertness, through the same sensitivity to change. If a familiar background stops suddenly, the nervous system may orient toward the new quiet. There is less sound, yet there is also a break in prediction. In most ordinary situations, this response is mild. The fan stops, the room changes, and the brain checks the new condition. If nothing else is unusual, attention settles. The silence soon becomes the new background. This sequence helps separate peaceful quiet from the idea of total sensory inactivity. Calm does not require the auditory system to stop responding. A calm nervous system can remain sensitive and flexible. It can notice a change, interpret it, and return to a resting state without remaining occupied by the event. A stable soundscape may support this flexibility by reducing the number of unexpected transitions. Soft rain, distant waves, or a familiar mechanical hum can create a broad and predictable pattern. Individual variations occur, but they remain within a range. The brain has learned to expect. Such sounds are sometimes used to soften other noises. A continuous background can reduce the contrast of doors, footsteps, or movement elsewhere in a building. The irregular events are still present, but their edges are less sharp against the surrounding sound floor. This does not mean that continuous sound is always beneficial. If it is too loud, too high in pitch, personally unpleasant, or difficult to control, it may remain demanding. Even soft sound can become tiring when it carries meaning that repeatedly draws attention. Speech is a common example. A distant conversation may be quieter than a fan, but fragments of recognizable language can be difficult to ignore. The brain is highly practiced at extracting words and voices. When speech is partly understandable, attention may continue trying to complete what is missing. A smoother, less meaningful background may be easier to release. The auditory system can classify it as continuous, without repeatedly searching for new information. This is one reason some people prefer steady rain or airflow when resting, while others prefer a room with very little external sound. Individual differences are important. Sensitivity to sound varies across people and across situations. Fatigue, recent noise exposure, expectation, mood, and familiarity can all change how strongly a sound is noticed. Setting that feels comfortably quiet on one evening may seem unusually active on another. The sense of choice can also matter. A sound selected intentionally may feel different from the same sound imposed by the environment. Turning on a fan creates a predictable event with a known source and an available means of control. Hearing an unidentified hum through a wall provides less information and less influence over what happens next. Researchers studying environmental sound often distinguish physical exposure from subjective response. Measurements of sound level and duration are essential, but they do not fully describe annoyance, comfort, or perceived disturbance. Meaning, control, timing, and personal context contribute to the experience. This is especially clear with sounds connected to valued activities. A clock in a family home, rain on a familiar roof, or quiet voices in another room may be associated with continuity and presence. Their acoustic energy may be modest, but their emotional meaning can make the environment feel settled. Other sounds at similar levels may suggest unfinished tasks, interruption, or uncertainty. The nervous system does not respond to vibration in isolation. It responds to what that vibration appears to represent. Silence carries meaning in the same way. A quiet room chosen for reading may feel spacious. A sudden quiet that interrupts expected activity may briefly feel incomplete. An empty building may feel peaceful in daylight and less familiar after dark, even though its measured sound level has barely changed. These responses are shaped by learning rather than by one universal meaning of silence. Repeated experience teaches the brain which acoustic patterns belong to ordinary rest, work, privacy, companionship, or waiting. Culture and household habits add further layers to those expectations. In some settings, quiet conversation communicates consideration. In others, lively sound signals warmth and social connection. A silent meal, a silent hallway, or a silent gathering can carry very different meanings depending on what normally happens there. The body interprets these meanings gradually and often without words. When the setting matches expectation, breathing and attention may remain steady. When the pattern becomes uncertain, awareness may narrow until the change is understood. This does not imply that every small acoustic change produces measurable stress or lasting effects. Most changes are brief and ordinary. The nervous system is designed to orient, evaluate, and adjust many times throughout the day. A moment of increased attention is not the same as harmful stress. Longer or repeated exposure to unwanted sound is a different question. And research continues to examine how intensity, timing, sleep disruption, perceived control, and other factors interact. Careful interpretation is necessary because sound environments are complex, and people differ greatly in their circumstances and responses. For the quiet listener, the important point is gentler. Calm is not created simply by removing every sound. It often emerges when the acoustic environment is steady enough to understand and soft enough not to demand continuous attention. Within such an environment, hearing remains active. It notices the beginning of a sound, follows its pattern, and observes its end. The body may respond briefly, then settle as the event becomes familiar. Quiet is preserved not by perfect stillness, but by the ease with which each small change can be received, interpreted, and allowed to pass. Silence becomes easier to understand when it is no longer treated as an empty space. It is not simply the absence of voices, music, traffic, or machinery. It is a changing relationship between the sounds that remain, the sounds that have stopped, and the attention that moves among them. A quiet place still contains a world of vibration. Air passes through narrow spaces. Buildings expand and contract with temperature. Leaves shift, water moves, distant engines fade, and the body continues its small rhythms. Much of this activity remains outside awareness. Not because the ears have stopped perceiving it, but because the brain has learned which patterns can safely remain in the background. This filtering gives silence much of its softness. When sounds are steady, familiar, and easy to interpret, they require little attention. They become part of the setting rather than separate events. A room can therefore feel silent even while ventilation hums. Rain touches the window, and distant traffic moves beyond the walls. What matters is often not the total amount of sound, but the way sound changes. A sudden noise interrupts a pattern, but so can a sudden pause. The refrigerator becomes noticeable when it stops. Rain attracts attention when its rhythm breaks. A familiar conversation leaves a brief impression when every voice becomes still at once. The brain is sensitive to these changes because hearing is a system of comparison. carries a small record of the recent past and uses it to estimate what is likely to happen next. When the world continues as expected, attention can remain wide and gentle. When the pattern shifts, awareness turns toward the difference for a moment. Most of these moments pass easily. The new condition is examined, placed within a familiar explanation, and allowed to recede. The nervous system does not need perfect certainty about every sound. It needs only enough information to decide that the environment remains coherent. In this way, peaceful quiet is often supported by understanding. A known hum, a familiar creak, or the soft rhythm of rain may offer continuity. The soundscape confirms that the surroundings are behaving in an ordinary way. Even when individual sounds appear, they belong to a larger pattern that has already been learned. Unfamiliar silence may feel different because the pattern has not yet been established. A new room has its own reflections, distances, and hidden sources. At first, the brain listens more closely. It notices movement behind walls, changes in airflow, and sounds that travel through floors or ceilings. Gradually, these details form an acoustic map. The room becomes less mysterious, and its silence becomes easier to inhabit. This learning is quiet and automatic. It happens in bedrooms, libraries, forests, trains, offices, and houses visited only once. The brain listens for repetition, groups sounds into sources, and estimates which changes matter. With time, separate details blend into a stable whole. The experience of silence also carries memory. A particular kind of quiet may recall early mornings, winter evenings, empty classrooms, long journeys, or familiar rooms after everyone else has gone to bed. These associations can influence the way stillness feels before any deliberate thought appears. For one person, a distant train may belong to the sound of home. For another, the absence of traffic may provide the deepest sense of rest. Some people feel comfortable with a fan, rain, or quiet music nearby. Others prefer the softest environment available. Neither preference reveals a universal truth about the nervous system. Each reflects a different history of listening. Culture and social experience shape silence as well. A pause can express care, thoughtfulness, respect, uncertainty, distance, or companionship. Two people may sit together without speaking and experience the quiet as full rather than empty. In another situation, the same absence of speech may attract attention because words are expected. Silence, therefore, does not carry one fixed emotional meaning. Its meaning develops from place, timing, relationship, and expectation. It can feel restorative, ordinary, unfamiliar, intimate, or spacious. These experiences overlap, and they may change from one day to another. Scientific research can measure sound levels, brain responses, attention, and patterns of physiological arousal. It can examine how predictable sounds are processed, how repeated events fade from awareness, and how interruptions attract attention. Yet the complete experience of silence cannot be reduced to one measurement. It emerges from the meeting of acoustics, perception, memory, and context. Claims that silence automatically heals the brain or produces guaranteed benefits go beyond what careful evidence can support. Quiet may help some people rest, concentrate, or recover from demanding environments, but its effects depend on circumstances. A chosen period of stillness is not the same as unwanted isolation. A peaceful room is not the same as a space that feels uncertain. The word silence covers many different conditions. What can be said with more confidence is that the auditory system remains active within quiet. It continues receiving, sorting, predicting, and comparing. The ears do not close when sound levels fall. The brain does not become blank. Instead, listening becomes finer, and signals that were previously hidden may rise gently into awareness. This is why deep quiet can reveal the body. Breathing becomes clearer. Fabric moves with greater detail. A swallow, a shift of posture, or the pulse carried through a pillow may briefly appear. These sounds are not intrusions into silence. They are part of the acoustic world that louder surroundings usually conceal. Over time, even these signals may soften again. Attention turns elsewhere, and the brain allows them to return to the background. Silence continues changing without appearing to move. One layer becomes noticeable, then another. A distant sound fades. The room settles into a new balance. Perhaps the most accurate way to imagine silence is not as a perfect void, but as a spacious soundscape in which very little demands a response. The environment remains present, yet it does not press strongly against attention. The brain continues its watch, but the patterns it receives are gentle, familiar, and easy to release. In such moments, quiet becomes less about removing the world and more about hearing it without urgency. The room has its tone. The night has its distant movement. The body has its steady rhythms. Each sound appears within a wide field of stillness, remains for a while, and passes without disturbing the whole. And as the smaller sounds gradually return to the edges of awareness, silence no longer seems empty. It becomes a calm arrangement of presence and absence, prediction and memory, listening and letting go. The world continues in soft vibrations, while attention rests lightly among them.